let's get another example under our belts. And it looks like I went from example 1 to example 3. I don't know where example 2 went. I guess that's the way of the world sometimes. So, let's start with reading this problem. Find the volume of the solid that results when the region enclosed by the given curves is revolved about the x-axis. One of the curves is y equals x squared plus 1, and your boundary lines are x equals -1 and x equals +1. So I'm going to draw this fairly large, okay? This will be my x equals 1 boundary. This will be my x equals -1 boundary. And then the curve is x squared plus 1. So that's going to be a parabola that's been shifted up 1 unit. Y equals x squared plus 1. And we want to take this parabola and revolve it around the x-axis, because that's what it's told. If you need to pause and write it down, go for it. So when we take this parabola and rotate it around the x-axis, it's going to have a reflection that looks like this. This will be what the bottom of it would look like. And this revolution, so taking this curve and just spinning it around the x-axis, spinning it around, it's going to create circles, like so. And this time it's going to be kind of like a weird double-sided megaphone kind of shape. A little more challenging to draw. So when we look at this, it's going to end up being really wide on 2 ends and narrower in the middle. Kind of like a wormhole, like you would see talking about time travel. I don't know. I'm on cold medicine. I might sound a little crazy. But here's the deal. Each of these circles formed by rotating has a specific area, and that specific area will consistently be determined with a radius. And that radius for every single one of these circles is going to be determined by y equals x squared plus 1. So each area will be pi r squared. And this one is where I see a lot of students make a small error that has big consequences. You need to write this out. X squared plus 1 times x squared plus 1. Pi times x to the 4th plus 2x squared plus 1. Do not make a mistake of thinking you can distribute a power. You cannot. A power is a command, not a distributable constant. So now we've got an area for a circle. Volume is going to be the accumulation of that area. So for this problem, our volume is going to be, now you've got 2 options here. I'll walk you through both of them. Integrating from -1 to 1 of pi x to the 4th plus 2x squared plus 1 dx, or because this is perfectly symmetric, that is not a symmetric line, but because this is supposed to be perfectly symmetric, you can cut this in half at 0, the origin, and just double half of the integral. Instead of doing -1 to 1, because this is perfectly symmetric, you can cut it in half at that origin line and double the integral. So 2 from 0 to 1, and I'll take the pi out as well, x to the 4th plus 2x squared plus 1 dx. And then this is just regular old integration here. So the volume of this funky looking, I don't know, you tell me what you want to call it, shape is going to be 2 pi x to the 5th over 5 plus 2x cubed over 3 plus x from 0 to 1. And we'll get 2 pi 1/5 plus 2/3 plus 1. Oh, you guys know me. I don't like having to do the common denominators for algebra here, but it looks like we're going to. 2 over pi, or 2 pi. All right, let's hit this with a 3. Let's hit this with a 5. And let's hit this with a 15. All right, so we've got 3 plus 10 plus 15 all over 15. 3 plus 10 plus 15 is what, 28? So we've got 2 pi times 28 over 15, which gets me 56 pi over 15. All right. There we go.